And so, all right. Or maybe we can just watch the video and then I don't have to teach anymore. That'd be nice. Okay, we're back online and maybe I'm gonna risk it. Okay. Okay, we're good. No more nonsense. Okay, like I said, so if we increase this R, it becomes underdamped because when you increase R, the resistor in this particular circuit becomes less important. What do I mean by less important? Well, think about the edge case. If R is infinite, this is an open circuit, there is no resistor there, it's just an LC circuit. So as you increase R, you're going towards that open circuit scenario where the resistor is not even there. In contrast, when you increase R here, your edge case is that actually the resistance become more and more important. If this were to become an open circuit, all of the voltage will drop across the open circuit. And so just keep that in mind. You definitely need to understand how as you change R, you transition between these things for both cases. That's all I'm gonna say. I said a lot about this in the previous lecture, so if you're still confused, go back. Are there questions about this? Okay, so if we go from 1 ohm to 3 ohms, it becomes underdamped for the parallel case. Okay, nice. All right, in the interest of time, I am not gonna solve this circuit, but it's kind of written here, and I would study this, so I'll just say this at this point. There is going to be a question where I give you a differential equation, I give you some initial conditions, and you have to solve it. So even if you don't know how to apply KVL, KCL, you're going to need to know how to go from differential equation to this. Typically, we don't ask that, but since there's no Laplace, I had to add a question, and that's the question that got added. So, yeah. Okay, where do we go? So blah, blah, blah. Okay, this is like a Laplace question, so I'll skip it. Okay, so this is what I mean by you might see something that looks slightly different in an exam. So as you can see here, there's only one non-resistive element in this particular circuit, which means what's the order of this circuit? Yeah, it's a first order circuit. And additionally, can you get a critically damped solution out of this? No, you can't. Okay, good. All right, so for time less than 0, what's the quantity that we can actually use as our initial condition for time greater than 0? Well, the quantity would be IL, basically. So we need to find IL, and to find IL, remember that after a very long time, the inductor behaves as a short. And so what we have here is 18 volts. So here, I'm going to rewrite this. 18, 12, 12, and then 12, and then IL going through there. So we know that the current coming out of here is going to be 18 divided by 12 plus 12 in parallel with 12, right? That's the current being pulled out. So basically the total resistance divided by the voltage. So that's going to give me 18 over 18, which is equal to 1 amp. But then the current here gets divided into two parts. And because the resistances are the same, what would be kind of how much current would flow through each one of these branches? half the current. And so we know that IL will be equal to 1/2. So remember, IL would be the current going through this branch. Okay, so now we have our initial condition, which is that IL sub 0 equals 1/2. So is it clear to everyone how I got that the IL sub 0 is 1/2, or no? Yes, no, okay, cool. All right, so we have that IL sub 0 equals 1/2. Now we have to actually do the hard work of deriving a differential equation for this. Let's do this. So you can always use an R-Thevenin approach, but I'm not going to do that. But here we have kind of, let's just call this BB. And so we have kind of VB minus 36/12 plus VB minus VL/12 plus VB/12 minus 0 equals 0. So I just apply KCL in this particular equation. And what that's going to tell us is that VB 3VB/12 equals 3 plus VL/12. Or actually 36/12. So now we can just cancel out the 12s. So we get that 3VB equals 36 plus VL. All right, so now we need one more equation because we need to get rid of this VB. So what can we do here? VB. Dun, dun. It's a node equation. It's vector loop equations. I already used that. Yeah, so we can also use kind of this equation that basically VB will be equal to IL times 12, so the voltage from here to here, plus VL. And then we also know that VL is actually equal to LdIL dt. So that means that this is 12 IL plus 36 ddt of IL. So now we can just plug that back into here, and then that's going to give us our equation for And then this is also 36 ddt for IL. We can plug that back into there, and then that's going to give us an equation just in terms of IL. Is that clear to everyone or no? So if the voltage here is VB, the voltage here is 0, that means that the voltage drop from here to here, which is just IL times R, plus the voltage drop from here to here, which is just VL, has to be equal to VB. So that's how I got this second equation. And then if I plug this equation back into this equation, then I can get rid of all the VLs. So I'm just gonna show it on the next slide. So here's kind of the equation I wrote on the previous slide. And I guess I did something different, which I just said that IL was just BV minus VL over 12. And then I plug that in here. And then I can basically write this BB in terms of IL and VL. And then I got this equation. Okay, at this point, can everyone, once you get to this equation, can everyone analyze this circuit? Yes, no, maybe? Concerns? Okay, so there's also kind of a second approach, which is the source transformation approach, which basically you can sanity check your thing by finding what R Thevenin is looking into here. So remember, you would short this. And so R Thevenin looking into would be actually this one in parallel with this one plus 12. So 12 in parallel with 12 plus 12, which gives you 18. So really the equivalent circuit here would be you have a source, you have 18, and then you have 36 plus minus. And then the Thevenin voltage would be, I think it's just 36, I think. Okay. At this point, now you can actually just you can show that you can get the same answer if you were to analyze this circuit, basically. Questions at this point? No? Okay, cool. Next slide. Okay, so in the interest of time, I'm going to only go over the initial conditions for this one, and then I'm going to move on to convolution. So remember, to look at the initial condition for this, we have to assume the capacitor behaves as an open and the inductor behaves as a short. When you have these second order circuits, the critical thing is that the two things you can only define out of this is IL and VC. Those are the two things that you can actually transfer from the previous to the kind of the switch change state. And in this case, well, there is no current flowing through here, so IL will actually be equal to 0. And because there's no current, there's no voltage drop across here, so this is at 3 volts, and this is at 0 volts, and so VC has to be equal to 3. Now, let's say we wanted to solve for VC here. Well, we know that ILs of 0 equals 0, but that's also equal to the capacitor voltage, IC, of 0, which is equal to the capacitance times ddt of VCs of 0. So that's how you would get an initial condition for the derivative of the voltage. And then VCs of 0 would actually be equal to 3. So indeed, you have a initial condition for the voltage and its derivative. Now, if I needed an initial condition for d dt of IL, Well, I know that LdI/LdT is equal to VL, and that's really equal to, V in minus VR minus VC. Now, VR is actually equal to R times IL. VC is equal to 3 at time equals 0. And so I'm going to get that actually VLs of 0 here will be actually equal to 5 minus R times ILs of 0, which is 0, minus 3. So that's going to give me 2 volts. Now, I cannot say this enough. So here I have that VLs of 0 equals 0. Well, if you had used your initial condition as VLs of 0 minus, you would have gotten that your initial condition for VL is 0, which is not the case. Because as soon as you flip that switch, VL jumped from 0 to 2 volts. Because it's not a continuous quantity, basically. And so LdI/LdT is actually equal to 2 volts. Clear? All right. So once you have the initial conditions, you know solving this circuit is like solving any other circuit. You just go through the process. Okay. All right. Let's look at this one, which I think we looked at in the last lecture, but we can look at it again. Let's do this. All right, so remember, when we're analyzing these convolutions, we have to analyze this integral, e to the negative 5 tau, use of tau minus 2, use of t minus tau minus 3, d tau. So this one, remember, use of tau minus 2 is 0 whenever tau minus 2 is less than 0. Or another way to say that is when tau is less than 2. So that means that the integral from negative infinity to 2 of e to the negative 5 tau, use of tau minus 2, use of t minus tau minus 3, d tau, what's the value of that?
0.
Yeah, so this thing is 0. So 0 times 5 times e to the negative 5 tau is going to be 0. So that integral is just going to be 0. So we have that now plus the integral from 0 to infinity. Actually, let's not go to infinity. Let's forget about this upper limit for now. Okay, now let's look at this other unit step function, which will be 0 whenever t minus tau minus 3 is less than 0, which means that whenever tau is greater than t minus 3. So I just moved the tau to the other side. What does that tell us about the integral from t minus 3 to infinity of e to the negative 5 tau, use of t tau minus 2, use of t minus tau minus 3, d tau? What is the value of that?
0.
Yeah, so since this is 0, this whole thing has to be 0 because the product of 0 times anything is 0. So I don't even care what this is. This is 0. It's kind of like my bank account. I always tell people I'm a billionaire times 0. That's thanks to this teaching job that to live is to suffer. Anyway, yeah, so the only thing that's left to do is the integral from 2 to t minus 3, e to the negative 5 tau, use of tau minus 2, use of t minus tau minus 3. Now here's where we have to be careful, because if t minus 3 is less than 2, that means we've already integrated this range because we went from negative infinity to 2 already. So let's say t minus 3 is equal to, let's just say, is equal to 7, or sorry, negative 7. Well, that's already covered in the range from negative infinity to 2. So we would be double dipping kind of thing. And so as a result, we need to get rid of this integral contribution whenever t minus 3 or the upper limit is greater than the lower limit. So as a result, what we do to get rid of it is we multiply it by 0 whenever t minus 3 is less than 2. So whenever the upper limit is less than the lower limit, we have to multiply by 0. Another way of saying that is we have to multiply this by unit step function t minus 5. Okay, so this integral we don't have to do because remember it's 0. This integral we don't have to do because it's 0. We're left with this integral where it's just e to the negative 5 times 1 times 1. And our final solution will actually just be e to the negative 5 tau over negative 5 to t minus 3 use of t minus 5. That's it. Does this make sense to everyone? So you should be able to go through this logic. If you can, I can guarantee you 10 points on the exam, at least. Okay, so yeah, so then I basically took this and then I made it prettier or uglier depending on your thought process. Okay, a question for you. Let's say I asked you to draw use of negative tau plus 5. Can you do that? Okay, so just remember last lecture's example. There's the candy machine. I remember the candy machine, this particular candy machine, if you give it anything less than zero, so less than 0, so negative tau minus 5, it's not going to give you anything. And if you give it greater than 0, 5 plus, oh, there should be a plus, negative tau plus 5, it gives you 1. Okay, so what that's going to tell me is that the function is going to be 0 whenever tau is greater than 5, and it's going to be 1 whenever tau is less than 5. Okay, sure. So if this is 5, it's going to, oh, maybe not. Got the candy machine backwards. So it's going to give me nothing whenever I input anything greater than, whenever tau is greater than 5, and then it's going to give me 1. That's it. So just remember, look at your candy machine. So remember use of tau is, or here, use of x is 0 whenever x is less than 0, 1 whenever x is greater than 0, So use of negative tau ma plus 5, well, you just replace the 0, 1, negative tau plus 5, less than 0, negative tau plus 5, greater than 0. And then you can do a little bit of algebra with this so that you can get the right inequalities. I'm telling you this because I'm gonna ask, I haven't made the question yet, but I'm gonna test you on your understanding of these concepts. And I'm 99% sure that the result is not gonna be great. It seems like, why do I have to go through this extra step? This is like, you know why you have to go through this? Because it's gonna be crystal clear what you need to do. If you just try to like do it on the fly, your mind will play tricks on you. But this is kind of like moving this to the other side is not gonna lie to you. It's gonna automatically tell you whenever tau is greater than 5, it's 0. But in your mind, you might forget to carry the negative, and boom. Just putting it out there. Okay. 5 minutes. Yeah, so just remember, the impulse response was just you flip the switch. You replace your Vn with a switch that turns on at time equals 0. And then you put a unit voltage source. What that also means is that all initial conditions equals 0. So Vc will always be 0 when you have a unit step, and ddt of Vc will always be 0, and same thing with IL. Actually, no, not this one, sorry. Will always be 0 when you have a unit step response. Then you have to solve the circuit, you get your unit step response, and to get the impulse response, then you have to take the derivative of the unit step response. And remember also, when you have a delta contribution, you need to evaluate whatever multiplies it at 0 to figure out what that number is. It doesn't matter the value of that function outside of 0. That's it. And then after that is just some more convolutions that you need to do. Yeah. Okay, so if I asked you this question, can anyone figure out what the width of the narrower one is? What?
Still the same value.
The same what?
When the slope is equal to 0, like constant.
Okay, so here, right? So remember that the convolution would be the integral from negative infinities of piece of tau, W1, piece of t minus tau, d tau. Now, this thing is non-zero for a width of W1, and this thing is non-zero for a width of W2. So what's the maximum that this integral, what's the maximum like range for what this integral can be non-zero? Yeah, so basically the difference between the upper limit and lower limit, where these two things are both non-zero, is actually the width of the narrower one. You can't have the product of this be non-zero for a duration longer than the width of the narrower one, because this thing's just gonna annihilate it. Since both of these have a height of 1, the maximum this integral can be is actually the width times 1. So the maximum of this graph is actually the width of the narrower one. So W2 is equal to 3. Now, when you do the convolution, as time evolves, you can have one overlapping the other one, but then the amount of time that they're gonna overlap completely is how long it takes this edge to travel to this edge. And what's that width equal to? What is that overlap time equal to? Well, it's the difference in the two widths, right? So this distance from here to here is just W1 minus W2. So it's going to be flat for a duration of W1 minus W2. So since you know W2 and you know how long they overlap, which is for a duration of, is it 1? I think it's 1. Okay, so you know that W1 minus W2 equals 1, which gives you that W1 equals 4. Make sense, or? All right, that's pretty much everything in the exam. Yeah.
So what would you ask on the graph? Like in the example, what would you ask for in general?
I mean, those are the kinds of questions we would ask. So I could give you the two graphs and ask you what's W1, what's W2. Or I could multiply this by 3 so that then you have a 9 here. So you have to realize that you have to divide everything by 3. That's actually the next example. Yeah, that's pretty much it.